I welcome you for third session of fourth day of FDP on healthcare data analytics using artificial intelligence and machine learning. It gives me great pleasure to introduce Dr. Rajarshi Gupta. Dr. Rajarshi Gupta is currently professor with the Electrical Engineering section and head Department of Applied Physics, University of Calcutta. His primary research areas includes biomedical signal processing and analysis and intelligent health monitoring. He has 27 publications in reviewed journals and 43 in conferences, 7 book chapters with the Google Scholar citation of 938. Currently guiding 5 PhD students and completed two PhD guidance. He has completed 3 research projects as PI, co-PI, deputy coordinator with total funding of rupees 74 lakhs in the own area from UGC, DST, West Bengal, and currently associated as PI and co-investigator with 2 government research projects with funding of rupees 22 lakhs. Currently, he is serving as an associate editor of IEEE Transaction on Instrumentation and Measurement and an editor board member of Physiological Measurement. Today, he is going to speak on ML applications of biomedical signal analysis. Now, I request Rajarshi Gupta, sir, to take over the session. Over to you, sir.
Thank you. Good afternoon to all. It's my pleasure to join this session. At first, I would like to thank Dr. Uttam Chaskar and the College of Engineering and Management, Pune, for inviting me for this session. And I will be talking about, can I share my screen, Dr. Chaskar?
Yes, you can share your presentation as well, sir. Yes.
Is it visible to all?
Yes, it's visible, sir. Yes.
Okay. So, the title of my deliberation will be Improving Quality in Variable Biomedical Measurements by Artificial Measurement Techniques. So, before going to the details, let me tell you that now we are in an era where self-enabled measurements are possible. This is many of us are using smart bands or many self-monitoring systems, self-health monitoring systems. So naturally, whenever we are using such type of gadgets, so these gadgets, what they do, they collect physiological signal, and naturally most of the cases, these gadgets are connected via Bluetooth or some other link to our mobile phone. So naturally, ultimately these data are going to the web somewhere they are going to the web. Now, this group of sensors which are connected in gadgets like mobile phones, like smart bands, wristwatches, so they constitute the group of wearable biomedical measurements. Not only these can be owned by in hands or other body places, but now it is possible to have wearable vests, and from these there are many applications like space applications, military applications, firefighting applications, where these wearable biomedical measurements are possible. So, okay, so now the concern is that whether these measurements that are being taken by the sensors, these are collected by the sensors, whether they are worthy of processing. Because if these are of poor quality, naturally there will be measurement errors. And in many cases, there are automatic measurements for some basic preliminary level diagnosis. So naturally, if these measurements are not worthy of processing, naturally there is a risk of misdiagnosis or whatever inference that is taken by an automatic device, any software, or the human being like a physician will be erroneous. So naturally, for the last 6-7 years, there has been intensive research on this quality aspect. That means whatever the measurements are being done by wearable biomedical sensors, whether these are of good quality. Only when these are of good quality, then it will be processed for the further stages. And when these are of poor quality, they can be simply discarded. Okay, so this is basically the context of today's deliberation. Okay, so with this, I have divided this talk into two parts. One is part A and part B. So in the part A, I will be talking about basics of M-Health. M-Health is mobile health, and the basics of the two physiological signals that we consider mostly for wearable biomedical measurements. One is PPG signal, which is called photoplethysmograph or photoelectric plethysmograph, and another is electrocardiography or ECG. I think ECG is more or less common to all, because many of us are conversant with what ECG can provide. Then I will be discussing on wearable biomedical sensors and the issue of quality. And most of these quality issues comes from artifacts, which are basically unwanted signals, noise. So many of these signals, due to artifacts, they become corrupted. Not only corruption occurs due to the presence of noise, like hand movement, but also a part of the quality issue comes from the loosening of the sensors. Okay, so there should be a proper policy guideline, whether we will denoise the signal, corrupted signal, or discard the signal. What are the issues that we must consider depending upon different context of the measurements that I will discuss. Then quality assessment, how we can define a quality measurement in the perspective of biomedical signals. Mostly, as I have already mentioned, I will be discussing mostly these two signals, photoplethysmography and electrocardiography. And I will conclude part A with basic two approaches of signal quality analysis. Maybe we can take a short break. Then I will be going to part B. Okay, so with this, let us start part A. So now we are in an era of this M-Health. M-Health is an extension of E-Health, where the biomedical measurements, whatever data, physiological data that we collect from the human body, these are electronically assessed and electronically stored, electronically communicated. So if we consider that this is a human body, then these are the signals. Typically, I have shown some of the signals that we collect from different body parts. And in most of the cases, the mobile phone or the PDA or the tab of the person or the subject under investigation that is collected, then in many cases it is delivered to a cloud-based service, and this cloud-based service is or transparent to a server, a clinician, or if there is any ambulant situation. So from the ambulance also, these physiological parameters can be delivered to the cloud. So basically, this is a framework where now it is possible to monitor a person when he is in mobile condition, like when he is walking in his home, when he is sleeping, doing some basic activities, even when he or she is exercising, doing some exercise. It is possible to monitor the records. But in most of the cases, there is a web-based solution that is connected, that connects a remote clinician for these measurements, or periodically the clinician basically provides some feedback. It is also possible to have, nowadays we have many intelligent softwares also. As you might have seen MI band 4, band 5, many companies, Fitbit, they are commercializing these utilities, because we spend now much more on our healthcare. Okay, so there in many cases you will find that in the software there is a provision to provide some basic feedback, like how many steps we have run or walked in a particular period of the day, what is our sleep score, what is our heart rate, even blood pressure, anxiety level, sleep score in terms of bad, medium, or good. These are possible. So these mechanisms, they are inbuilt within the mobile phone, and they basically provide us a feedback from the system itself. So basically 30 or 40 years back, which was the system was on hospital based monitoring. So at that time, so a patient or a person has to be admitted in a hospital for monitoring. Now it is possible with the help of information and communication technology to monitor a patient remotely. Now I will be discussing two technologies. One is for mHealth, and the most important part is wearable biomedical sensors. And it basically says measurements on the go. That means a person who is moving or doing some activities. So these wearable sensors provide us the measurements when the person is active in his daily living. I have given some cases like a firefighter, like a gamer, then mountain climber, car race driver, and so on. Especially in basketball and football, these are coming rapidly. So the basic attributes or advantages that we get on wearable biomedical sensors are these are lightweight, low form factor, that means this should be of very small size, comfortable, reconfigurable means basically the different types of functionalities can be changed remotely. Multifunctional, a single sensor can provide two or more measurements. Like using the concept of soft sensing, now it is possible to use a single hardware sensor and infer more than one quantity. For example, if I get a concrete example, if we measure ECG, from that ECG, it is possible to derive the respiration. I think some of you have gone through the papers which is called EDR, ECG derived respiration. So that means for measuring the respiration of a person, we don't need to put up that chest on piezoelectric type sensor. Just measuring the ECG from the RPK amplitudes and many other ways by using the techniques of digital signal processing, it is possible to measure respiration. Likewise, there are many other soft sensing applications. In fact, PPG is a signal from which we can measure 6, 7, 8 parameters. It is possible. An essential component of all such wearable biomedical sensors will be low energy, and also this high computing ability. Now, what are the advantage of this low energy? If the system is of not of low energy, then the battery power will be drained very quickly. So there are different strategies which are adopted. For example, duty cycle modulation is a technique by which the energy consumption can be substantially reduced. And high computing capability means we talk about on-device measurements. That means the point at which the measurement is done, that means the sensor is connected, that is on the human body, just after the collection, we can make some immediate measurements. Now that is possible if the system, that is the portable hardware module, contains a powerful microcontroller. So these are the basic attributes of wearable biomedical sensors. And this slide shows basically the growth of mobile phone for over the years, like in 2020 to 2025. You can see that for the last 10 years, we have a huge surge in the use of mobile devices, and since almost 8 of 10 persons in city-based population uses commonly a mobile phone, then the mobile device of the subject or human being can be used as the acquisition device, number one. Number two, it can be used as the computing device for making some basic measurements. And number three, since all these mobile phones are now data enabled and having many communication channels like Wi-Fi, Bluetooth and others, so these can be also used as a gateway to upload the data in some secure servers. And since we are now in Android operating system, so user interface is very powerful. These are very this user friendly, and as I have already mentioned, so the connectivity is another strong part of using the mobile phones. Now I directly start with photoelectric plethysmography or photoplethysmography signal, because in the part B of my discussion, this signal will be the basic signal that I will be dealing with. So this is basically, there are two technologies. I think many of you are already conversant with this PPG technology. So there are two modes. One is called propagation mode and another is called transmission mode. And what is done, there is one LED and a matched photodetector. So in transmission type, this is the wavelength that is used, and in the reflection type, this is the wavelength that is used. And the basic principle is that whenever our heart pumps the blood in our peripheral body parts, like our forehead, like our toes, like our fingertips, any peripheral part of the body, synchronous to the, with a certain delay, synchronous to the heart pumping action, there is an increase and decrease of blood volume. And this increase and decrease of blood volume is manifested by this curve. This curve is based on the fact that when there is an increase in volume, if you consider that transmission type technology, then the most of the energy is absorbed here in this blood full or oxygen rich blood when there is an increase in pulsatile blood flow. When we consider the reflection type technology, basically what happens is that these blood cells acts as a small mirrors. Okay, and so there is larger reflection of light and the intensity at the photodetector increases. So by these two techniques, it is possible to generate a waveform which is called photoplethysmogram or photoplethysmography waveform. So it looks like this. Basically, there is up to this, from the starting phase, this part is uprising. This is the ventricular systole. That means when the ventricle pumps. And the after part, this part from here onwards, it is called diastole. That is when the ventricles are basically expanding. Now I have shown some of the morphological features that we called PPG features, time domain features, which are very much important for certain physiological measurements. Like for example, if we consider that this is this height, that means from the baseline, this height is a direct measure. It is directly proportional to the blood pressure, arterial blood pressure. There are many other parameters which I have shown here, like PPG. So, the most prominent use of PPG is blood oxygen saturation, which is called SpO2, then heart rate, then respiratory rate and respiratory signal. Recently, there have been many works on PPG based blood pressure measurement. This is one prominent area of research, PPG-based blood pressure measurement, then cardiac output, arterial compliance and aging. Basically, this is what is meant by arterial compliance. Basically, with our aging, the elasticity and flexibility of the arteries get decreased. So various features of PPG can be used to determine the arterial compliance, or which is also known as vascular compliance. And many parameters can be measured. And these are basically some of the features like systolic amplitude, pulse width, peak to peak time, crest time. This is dicrotic notch amplitude. This is the dicrotic notch. This is the dicrotic notch, and this is the diastolic peak. Then diastolic peak amplitude, augmentation index, many these features are useful for many types, for deriving some surrogate measurements that I have shown here. Okay. ECG is, I think, much more common to us because there has been intensive research, many researches over ECG than PPG. In fact, over the last 40 years, there has been extensive research on ECG. So this waveform, I think it is known to all. This is P wave. This is QRS. This P wave represents atrial contraction. This QRS represents ventricular contraction. And this T wave represents ventricular expansion. And you can see that I have marked many physiological features, so which are helpful because basically there is basic difference between ECG and PPG, because in the case of ECG, the cardiologist, since it is a direct physiological signal of endogenous type, so the cardiologist directly measure this heights, durations, wave intervals to infer about various cardiac abnormalities. Okay. So there are many ECG derived clinical parameters also, like heart rate, as I have already mentioned, respiration, cardiac functions assessment. A major part is called rhythm analysis, or we call this arrhythmia analysis. So there are many types of arrhythmia or irregular heartbeats. I have shown some of the figures, like this represents premature atrial contraction. This is premature ventricular contraction. And you can see that this is first degree atrioventricular node block. So there is no QRS. So like this, many cardiac functions can be assessed. Like if we talk about cardiac disease analysis, then infarction, ischemia, these are the main diseases. Infarction is manifested by this elevation or the lowering of the ST segment in certain times. Okay. Let us move on, because these two signals I will be using mostly. Now, let us come to some idea of wearable biomedical sensors. I have shown some of the pictures. You can see that what is the size of the sensor? Extremely tiny. These are called patch type, and it provides on-body sensing. So this is the diagram. This is the diagram of this band type wearable sensor. You can see that within this short area, 60 by 20 millimeter, there is not only the sensing part, but also this additional components like energy harvesting, this RF antenna. Now this energy harvester is used for collecting energy from the ambient sources or resources, like changing magnetic field, maybe sunlight, or some other RF sources. And this energy harvester basically powers up the battery, this small lithium-ion battery or cadmium cell battery. And these are some of the diagrams I have shown. Like this is a typical inertial measurement units which are installed in the different portions of the limbs. And from these, you can see that it contains the sensing unit, the signal conditioning unit. As you know that most of the biomedical signals are basically very low in amplitude, like in microvolt or millivolts. So naturally, we need to boost up the signal energy, as well as we need to provide some denoising operation. So all these units, they contain the sensing part, the signal conditioning part, then the digitization, then a microcontroller, then maybe some Bluetooth module or radio chip if some other type of radio communication is required, and this is the antenna. So you can see that with respect to the proportion of the hand, what is the size of a wearable biomedical sensor. So in this diagram, here is a PCB I have shown. There are different types of sensors like temperature sensor, potentiometric sensors, bioimpedance sensors. There are other sensors as well. And this is a stretchable on-body multi-parameter sensing. That means if the body, skin, since these are fixed or fixed on the human skin, and during our daily activities, the skin can stretch. So this two things are to be considered. One is that there should be no adverse effect on the skin. Second is it should be stretchable so that it is not detached during exercises or any other activities. Okay, so any questions from the audience, because I want this session to be really interactive in nature. So if you have any questions up to this point, just feel free to ask. Okay, if there is no question.
Hello, sir.
Yes.
Yes. Can you elaborate EEG signals as well along with ECG?
Actually, madam, see that EEG signal, I think you know the basics of EEG signal. Okay. But as far as wearable biomedical sensing is concerned, EEG signal is rarely used for wearable sensing. See, actually for wearable sensing, what I am discussing is basically in the context of wearable sensing. In the case of wearable sensing, the most common signals which are collected, these are ECG, then PPG, then inertial measurement unit, that is, I think you know the name of gyroscope sensors or accelerometer sensors, okay, or tactile sensors. So these are the common temperature sensors, then EDR signals like electrodiagonal activity. The other name is GSR, galvanic skin response. These are the signals which are most commonly collected as far as wearable biomedical sensing is concerned. Okay.
Okay, sir. No problem.
Fine. Any other question, or can I proceed?
Yes, sir, you can proceed, sir.
Fine. Okay. So now we talk about, with this basic introduction, let us talk about the quality. Now we come to what is quality in wearable biomedical measurements, and most of this quality are induced by what is called artifacts. Okay, like in the case of ECG signal, we have 6-7 types of artifacts. For example, muscle noise, baseline wonder, then electrode pop or contact noise, respiration, and others, power line interferences. Now, I have shown one signal frame. So in the bottom part, you can see what is the reference ECG, because when we talk about the quality, it is very essential that the reference signal, that is the clean signal, that should be available, because quality is a relative term. Okay. So as you can see that in the middle graph, in certain portions, we have the muscle noise. Mostly the muscle noise comes in the range of say 70 Hz and above, mostly in the kilohertz range also. Okay. So this portion, there is a question over the quality. In the first one, topmost one, the baseline wonder is shown. Basically, in the case of baseline wonder, what we see is that the baseline of the ECG, if we draw a graph of ECG, so this is the baseline. So the baseline becomes modulated with a slowly varying respiration signal. So this is the baseline on which the ECG signal is modulated. So like this. What is the problem with the baseline wonder is that when a cardiologist basically inspects an ECG, he or she frequently measures many of the wave features like QRS amplitude as I am showing, then T wave amplitude, then certain intervals like QT intervals, something like this. In the case of time axis measurements like QT interval, ST segment, so if the baseline wonder is there, it becomes very difficult to get the amplitude measures. So quality issues are there with the baseline wonder also. Okay, so this is the case of an ECG. Here I have shown the case of a PPG signal. So this is the reference signal which is shown in the green, and this is the typical PPG cycles. And the uppermost one is partly clean. Why we are calling it partly clean? Because at least in this waveform, you can have a vague idea of where the systolic peaks are there. I will come to this point later on. So there will be how to define a diagnostic quality measurement and a basic quality measurements. So in the case of partly clean, the criteria is that at least you can detect one fiducial point, which is the, in this case is the systolic amplitude, systolic peak. In the noisy signal, you cannot assess anything. The full signal is corrupted. And let me tell you that in the case of PPG signal, most of these artifacts comes from the movement of the body parts where the PPG sensor is attached. Normally, ECG sensors are mostly chest on. So there is not much body movement. But see, whenever the PPG sensor is on a finger and a person is doing normal activity, then this hand movement will invariably occur. So whatever communication goes, say this is the sensor. I think due to this COVID pandemic, we now know very well what is a pulse oximeter. It is very common to us now. So you can think of a pulse oximeter that is basically measuring the basic PPG signal. So in the pulse oximeter, if there is any Bluetooth communication from which you can connect the signal to your mobile phone, and these are the qualities of the signal, especially for the partly clean and the noisy signal. So whatever you will be measuring, like heart rate, like SpO2 or pulse saturation, oxygen saturation, or BP, all will be erroneous. So basically, we define quality in variable biomedical measurements like that. The quality of a variable biomedical measurement will provide the assurance or reliability that we can guarantee while we are doing automatic measurements. So this is basically the notion of quality in variable biomedical measurements. I have shown two examples, one with the ECG, another with the PPG waveform, and I have shown some basic issues with the quality. Any questions? Okay, let us proceed. So whenever we are working on quality in variable biomedical measurements, it is very important to establish the ground truth. That means what is true. And let me tell you that this ground truth has to be established by a qualified physician or a very experienced researcher. In this slide, I have shown one reference template. As I have already mentioned that whenever we are talking about quality, the reference or the clean segment of the signal, whether it is ECG or PPG or someone other else, the reference template must be shown. And here you can see that this picture is from one of our researches. So the doctors, they were told to manually annotate the signal. So this annotation is provided by a qualified cardiologist or a physician, and he or she will provide which are the pulses, like here, or here, these pulses are not acceptable. So here also some pulses are not acceptable. So here you can see the pen marks where these pulses are not acceptable to us. So if we think of researching with the signal quality assessment, the first thing we have to do before doing any machine learning applications or anything, first we have to annotate the data by a qualified physician. That is very, very important. Okay, because whenever we will be training the classifier, these annotations will act as the ground truth. Okay, the second thing is that these annotations are purely subjective. Purely subjective. That means it can vary from one person to other. So to one doctor, one pulse may appear as clean, but to the other doctor, that pulse may appear as corrupt, because this type of inspections are always subjective in nature. So what is done is that you have to annotate these signals with more than one physician. Even then, you cannot accept or take all the annotations, because there will be conflict in certain segments of the data where one physician will tell you these are acceptable segments as far as quality is concerned, and the other physician will discard them. So the best practice is, whenever you do go for researching or signal quality assessment, take adequate data, and using some statistical sampling, you show these data to the cardiologist or some expert physician and consult two physicians. And finally, the segments where you have conflict from both these physicians, you need to discard those segments. So you can only use these segments where both physicians have the agreements. Okay, so this will provide you the ground truth, because for training of the classifier, I will be discussing later on, you need to provide this ground truth for every subject. If you are collecting the data from say 100 subjects, so for every subject, at least 20 to 30% of the data, considering the total time interval of collection. Suppose you have collected the data for 7 days. So from each day, 30% of the data, you must get these annotated by some expert physician. Okay. Now, let us talk about effects of artifacts. So what the artifacts do? Basically, I have shown using an ECG signal. So this is a noisy signal. And using denoising, if we go for denoising, you can see that the reference signal and the denoise signal are almost superimposed. So denoising operation in some cases can retrieve the original signal from the ECG, but it is not true. Where we have loose contact, that is indicated by this electrode pop or contact noise. So that means the contact has become, the electrodes has become loose from the skin, and as a result of which, especially during this segment and these segments, it has become corrupted. Now, it is to be made very clear that in these cases where the signal is not there, you cannot retrieve the signal by any denoising operation. So the first thing is that whenever we are talking about quality, when I have enough data, in certain cases, if the signal is corrupted, like say here I have shown power line interference, it is possible to retrieve the signal by a suitable denoising operation. Many types of denoising operations starting from digital filter, now wavelet, EMD, VMD. These methods have become very popular. Singular spectrum analysis for ECG, these have become very, very popular. Principal component analysis, there are many methods. But let me tell you very clearly that you cannot retrieve the signal where the signal does not exist. And that example I have shown here in the case of electrode pop or contact noise. So the signal is absent here. There is no signal. So when there is no signal, there is no question of retrieval of the signal. Okay, fine. So if you have any questions, I want this session to be really interactive. So if you have any questions, just interrupt me if you need any clarifications, because this part A is very important and this will make the foundation what I discuss in part B. Okay. So if you have any questions, don't hesitate to just interrupt and tell me what is your query. So let us talk about unacceptable ECG segments. So these are basically unacceptable segments. I think it is a little bit of hazy. Why these are unacceptable segments? Say visually it may be difficult to identify these corrupted or unacceptable segments. So the second one, what I have done is that it is the HRV amplitude plot. So you can see that the HRV has gone down sharply and come up sharply. So within a small time, it is not possible to have a HRV fluctuation of almost 100%. Here also, there is a sharp fall. Here also, there is a sharp fall and also a sharp recovery. So if from the time domain representation of the signal, it is not possible whenever it is difficult to assess the unacceptable ECG segments. Sometimes these derived measurements become useful. Like for here, I have shown like plotting the HRV amplitude. Okay, in the second case, you can see that signal loss due to loose contact of the sensor, which I have already mentioned. Loose contact. So here there is no signal. In this, it is flat. Sometimes it may happen that signal may get saturated at 5 volt or something. So because if the patient suddenly moves, there may be certain saturation at 5 volt. So it is the case where there is no signal. That means the contact is totally lost, and in some cases there may be complete saturation of the signal, and this occurs due to the sudden movement of the patient. So here in these two graphs, you can see that in the upper graph up to this point I have shown in arrows, there is no signal, and here in this graph from this point there is no signal. So naturally, when we will talk about quality of a signal, not only the question of corruption due to the artifacts will come, but also the question of loose contact or sensor malfunction will also come. And we need to distinguish this, because when you have a flat signal, basically when you have an entirely flat signal, you cannot derive any feature. Normally, I think for the last 3-4 days, I think many of you are already conversant with this machine learning techniques, but I think I was going through the this lecture sessions. I think you have now adequate basics of what is a machine learning, because naturally in the case of when we want to apply a machine learning technique, naturally we have to extract some features. Now, whenever you are trying to extract the features from a flat signal, that means there is no signal, there will be no features. So there is no use of extracting features from a flat segment, either it is a zero amplitude signal or it is a saturated signal like here. So naturally, if you develop a signal quality assessment algorithm, then you have to check about these things, because normally what we do is that we chop the signal using certain windows, like say 1 second, 3 second, or 5 second, or 10 second, and simply we use some feature extraction tools like say discrete wavelet transform or autoencoder or principal component features, and just feed it to the classifier. Now my point is that before that you need to assess that whether there is any loose contact or sensor malfunction in the signal, because from the flat segment you will not, what you will get, it is basically a garbage. It is not a true representation of the signal. Got my point? So let us proceed. So here we will be how we can define the quality of a biomedical signal. So let us first talk about diagnostic quality measurement. So diagnostic quality measurement means full diagnosis can be done. So like here we have a P, QRS and T. This is the J point T, and you can accurately measure all the fiducial points like P onset. This is P peak. This is P offset. Then Q onset, Q, R, S. This is the ST or J point. Then T, T onset, T offset. So when all these fiducial points, I think you know what is fiducial point. Basically these R, then T, this P, then the onset, offset, these are called fiducial points. So when you can make all these measurement very reliably and accurately, either by using a computer algorithm or by visual inspection, this is called diagnostic quality measurement. So the basic criteria is that all the waves are clearly identifiable and cycle by cycle measurements can be performed. So there is something special on cycle by cycle measurements, because over the last few years there are many applications of what we call that bit to bit measurements. The most prominent example is bit to bit blood pressure measurements. That means how the systolic pressure and the diastolic blood pressure, they are fluctuating from one bit to the other. So whatever we measure in using oscillatory measurements is not a bit to bit measurements. That measurement is done over a period of say 30 or 45 seconds by occluding one artery and then releasing it and detecting some sounds. So in recent years there has been an interest on cycle by cycle measurements. So from that part of view, diagnostic quality measurements are very, very important. In the case of this PPG waveform, you can see that this is the PPG onset, or what is called foot. Then this is systolic peak. This is the dichrotic notch, which is visible normally in young adults, because with our age, this portion fades away. So this basically becomes flat. So this is the diastolic peak, and this is the thing. So compared to a PPG signal, an ECG signal is having much more number of fiducial points. Naturally, number of features will be much more. So the first quality measurements that I discussed is diagnostic quality measurements. Then comes the second, to some extent, the degraded or lower quality, which is called basic quality. Okay, so the basic quality of measurement is represented by, say, this is my reference, this is the reference signal, this is the reference signal, and this is the quality what we define as the basic quality. Basic quality means you can take some basic measurements, like see, some peaks are visible here, and if these peaks represent the R peaks, then probably you can make some basic HR measurements. That means number of pumps or cycles per unit time. And in the case of PPG also, I have shown that this is called the basic measurements. If these peaks are visible, at least you can calculate the HR, and you can also calculate the HRV, which is very, very important for many autonomic functions. This HRV it is an old area of research, and many prominent researches are available on HRP measurements. Okay, so we defined the diagnostic quality measurement, where all the waves are clearly identifiable and cycle by cycle measurements can be performed. And then the second or somewhat degraded quality, that is basic quality, where we can do some basic measurements. The last one, which is worst, this is unacceptable quality. Unacceptable quality signal, you can see that this signal has no, you cannot either using a computer program or using visual inspection, you cannot do anything. So this is called unacceptable quality. This is in the case of ECG, and in the case of PPG, you can see that, see, almost there is no information. This flat line represents no information. So this is called the unacceptable quality. So we defined three quality criteria or qualities. One is called diagnostic quality. The middle one is called basic quality, where we can do some basic measurements like HR. And the unacceptable quality, which is worst, we cannot make any measurements. But I'm again repeating, whenever we are talking about the quality, in any case, we need to have the reference signal. Reference signal means the claim signal. So whenever you go for annotation or any such type of operation, getting your data annotated, you must show the reference signal to the doctor, because what happens is that ECG and PPG, especially for the PPG, the morphology widely varies from one patient to the other. Even if the hand movement is not there, for some cases, you will find that the signal seems to be corrupted. There are many factors. Okay. So the reference signal must be shown to the doctor. An important point is that to consider is that since we know that in certain cases, we can denoise the signal. So the question is that when we talk about the quality, we need to judge or decide whether to denoise the signal or to discard the signal. And in either cases, what we gain or what we lose. Okay, so I have here shown 4 perspectives from which this decision has to be taken, whether to denoise the signal or discard the signal. The first and foremost thing that needs to be considered is how much data I have. Because the more data I have, the more leverage I can exercise on discarding some part. Suppose I have 24 hours of signal, and the signal in some cases, if out of that 24 hours, I have poor quality signal in say 2, 3, 4 hours, then I can easily discard that signal. And if I have only 5 minutes of signal, and out of that 2 minutes is of bad quality, I cannot afford to discard that data. So the first thing, whether to denoise or discard, the first aspect to consider, point to consider is that how much data volume I have. Number 2 is whether my measurement is real time, pseudo real time, or purely offline. So let us start with the simplest thing, because most of us engaged in biomedical research, we do this type of applications, purely offline applications. So what we do, we collect the data using a data acquisition card. There are many types of data acquisition card available in the market. We simply collect the data in a computer, laptop, whatever it is, and then we put them in some file format. Then we write some algorithm, maybe in MATLAB, maybe in Python, something. We just call the file, and make our measurements. So in academic research, 70 to 80% of whatever we do on any types of signal processing is purely offline applications. Let us discuss the next one, pseudo real time. Okay. Pseudo real time and real time, there is basically a very fine line of division between what is called real time and pseudo real time. And the difference basically depends upon the latency of the measurement. By latency of measurement, what I mean is that what is the expected output from my real-time processing that is allowed or allowable. For example, I am making continuous HR measurements from an ECG. So this is the consecutive cycle. So what we do, we will basically just pick up the RPICs and basically we will be calculating the gap. Okay, fine. So these gaps will give me the HR measurements. Now, what is the latency? The latency is that in which interval you need to provide this HR. If the latency is say 2 seconds, then naturally you need to have 2-3 measurements, that means 2-3 detections of consecutive RPICs, and immediately you need to calculate. So it is a real-time measurements. And pseudo real-time measurement is that if this time latency, that is the requirement from the system, that you after every 10 seconds you provide the heart rate, then at least you can go for 12 to 13 RPIC measurements and make an averaged HR. Say in 12 to 14 seconds, you are expected to get 14 to 16 RPICs. If you consider that you are dealing with a person's heart rate between 60 to 100 or something like this. So you make 14 to 16 heart rates, just make an average of these heart rates by the number of cycles, and you report a single heart rate after every 10 to 12 seconds. Then it is a pseudo real-time measurement. Okay. So basically defining pseudo real-time or real-time, what is the demand from the measurement? What is the latency that has been decided? Like I'm giving a simple example of pulse oximetry. Now, pulse oximeter is very common to us, and I think most of us have purchased one pulse oximeter due to this trying time last year or this year we had in our home. If you fix that pulse oximeter in your finger, you will see that on a colored LCD display, the value of SpO2, that is the saturated oxygen in your blood, that is being updated after every half second or 1 second. So that is the latency in which rate the display has to be refreshed. This depends upon from system to system. So in the case of, say, the example that I just discussed in the case of pulse oximeter, if I had to refresh the heart rate from in every 1/10 of a second, then our visual perception, there is a limitation of visual perception. We cannot properly see the change. So based on that, what is the requirement? What is the, like in the case of ICUs, when the data logging is done, the latency may be even less. Okay, so I think I'm clear what is meant by purely offline applications, pseudo real-time and real-time. Now, in the case of what we were discussing is whether to denoise or discard. Now, when I am doing for offline measurement, then I have ample data in my hand. If I have ample data in my hand, I can determine the quality and I can discard the data. In the case of real-time measurements or pseudo real-time measurement, if I need to judge the quality, then naturally it is very difficult to denoise the data in some cases. So in that case, maybe I have to discard the data because I am making, after all, continuous measurements. And this is related to what is pointed in on-device measurements. On-device measurements means within the device, there will be a microcontroller with some algorithm, and it will measure some parameter like heart rate, SpO2 or something like this at the point itself, like I discussed, say handheld pulse oximeters. So in the case of on-device measurements, there are certain issues. One issue is obviously is the latency that I discussed, latency. Another is that memory. Okay, this is a serious limitation because in on-device measurements, you are not using a full-fledged Pentium i3 or i5 processor, something like this. You are using a processor which is somewhat less capable or less powerful. And also, you can't have that GB level of memory. So naturally, you have to compromise between the memory and the latency. So whether to denoise or discard, that depends upon the latency and also on-device measurements. So where we have certain limitations of memory. So memory will be divided into one is putting the data and putting the code. So naturally you have to compromise. You have to take compromise between these aspects. The last one is application specific measurements. There are certain applications, like I told that in soft sensing applications, we take one measurement and from that measurement, we infer some other measurement. Like in the case of very prominent example is SpO2 measurements. Like in the case of SpO2 measurements, we have two sets of LEDs. Okay. And from these measurements, we basically measure the photoplethysmo graph. But from that, we calculate basically the saturated oxygen in the blood. So this is an application of soft sensing. Or for example, more sophisticated measurements like ECG derived respiration, PPG derived respiration, something like this. So in those cases, what to do when there is an issue of the quality? The signal is unacceptable. So many such issues are to be considered when we decide on whether to denoise the signal, if it is possible to retrieve the signal from the corrupted signal, or we can simply discard the signal. Okay, any questions? If you have any questions, you can ask. Yes. Yes, madam. Shobhak, fan tag to chali gayi beta. Any questions? Madam, I can't hear you properly.
Participants, you can unmute yourself and please you can ask questions.
Dr. Sunita, I think you were trying to say something.
The question answer asked.
Okay, fine. Should I proceed, Dr. Chaskar?
Yes, sir.
Fine.
I mean, what is late?
Okay. So now with the basic understanding of what is meant by signal quality, there are two basic approaches of signal quality assessment of biomedical signals, in particular variable biomedical signals. The first approach is bit segmentation approach. Basically, bit segmentation approach, what is a bit? Since I am largely talking on cardiovascular signals, so the origin of these signals is due to the pumping action of the heart. So here basically bit means one cardiac cycle. So in the case of ECG, that is the lower plot, I have shown this is one baseline and this is another baseline point. So between these 2 points, whatever we have, we can call them as a complete cardiac cycle. So you can mark these complete cardiac cycles. So in one approach where we call it bit segmentation approach, the first thing to do is that you need to delineate the cardiac cycles from the signal. Okay, and then for each bit, you need to provide the assessment or assess the each cardiac bit. In the case of PPG signal. So here, this is the onset point of the bit. That means it starts, basically, the cardiac cycle starts, ventricular contraction. This part is the ventricular contraction, and this is the relaxation part. So this portion constituting one systolic phase and one diastolic phase constitutes a bit. So either it is a PPG or an ECG signal, you need to delineate the bit. Okay, but the point is that under corrupted condition, bit delineation from the ECG or PPG is a separate research area to deal with. See, if you see in the literature, there are multitude of papers available on the ECG or PPG bit detection, especially under corrupted condition. So this is the disadvantage or the issue to deal with when the signal is corrupted. But once you delineate the bit, that means you extract the cardiac cycles, you can apply relatively simpler techniques for assessing the signal quality assessment. Okay, so this is the first approach that is normally followed in the literature. That is the bit segmentation approach. The second, so basically an extension of the bit segmentation approach I have shown here, that if we can take this sequence of bits and then you extract the bits and then align them with respect to the R peak. So here around 60 R peak aligned bits are shown, and if you have this reference ECG template, so what is done, this operation is called basically this cut and align bits. So from this cardiac cycle, you detect the R peaks and then you detect the baseline points in the TP segment, T and P, one wave P and the following wave P. So this is the T wave and this is the following P wave. So in the TP segment, you need to detect the baseline and then you cut these beats and align with respect to the RP. Okay, and you can make and when you plot this RP aligned ECG, if one bit is having corruption, that will easily come out something like this. And the best thing to judge is using a correlation best match. So if you just calculate the cross correlation between two things, these two arrays, then you can easily determine what is the signal quality. Okay, so here I have shown that these are the R peaks detected. So this is clean. Then here you can see this is somewhat degraded quality. This is more degraded quality. As we go down, then we have degraded qualities. And here on the right side, you see that in the case of a clean bit, the correlation coefficient, if we talk about Pearson's correlation coefficient, the formula is given here. So we can have the red color plot provides you the reference bit and the superimposed plots for gradually noisy signals. So here it is less noisy, so you have little bit of correlation, good correlation 0.1, it can be maximum 1. And then with gradual increase or the corruption level, the correlation coefficient is degraded. So this is one approach that is suitable when we go for this bit segmentation approaches. So that means the bits are detected, these are cut and aligned to create a superimposed impression. And if we have the reference template, we can calculate the correlation coefficient between the reference bit as well as the individual bit. So based on this, the individual bits can be assessed for their quality. Now, in the case of PPG signal, the basic approach is same. So basically here also, these lines basically show the bits or segmentations. So this is the average template or you can call it the reference template, it is clean, then you can calculate the correlation with this reference template with the individual bits. So that is also possible. Okay. So the basic principle of template matching, the essence of template matching is that you delineate the bits, then you align them with respect to some fiducial point. Most common approach is this R peak or the systolic peak of the PPG, and then you calculate the correlation coefficient. Then we come to the other approach, which is called non-segmentation approach or bit non-segmentation approaches, where due to the noise corruption, it is very difficult to calculate, to delineate the bit. See, if you consider the lowermost signal over here, this signal, it is impossible almost. It is impossible to calculate the individual bits. So for those cases in the literature, the skewness and kurtosis are two parameters which are found very useful. So in many little bit old literatures, maybe between 2005 to 2012, we find that many of the approaches, they used this distribution, they plotted the distribution, and then from the skewness or kurtosis, say you take say every 3-second data here, chop it, and then plot the samples as distribution samples. So here these are the amplitudes, not the time. So these are the amplitudes, and this is the number of samples having this much of amplitude, something like this. So if from this approach also it is possible using the skewness and kurtosis, it is possible to assess the signal quality using non-segmenting approaches. Now we come to what are the computational intelligence based approaches. So I have given a typical signal flow diagram. So for an input data, we need to segment. Whether this segmentation will be based on bit based or non-bit based, that depends upon your approach. But the first thing you have to do is that whatever you do, whether it is a bit segmentation approach or non-bit segmentation approach, you must annotate the data by experts. Then you can have your data splitted for testing and training. So if you have a classifier that needs to be trained, if it is a supervised pattern classification, then you need to train that classifier. For that, you can take 50% of the data to train the classifier, and the rest 50% of the data can be that is used for the blind test. Then from this, you need to extract some features, relevant features. This is optional. If you have huge number of features, then you can go for feature minimization or feature ranking, or what we call feature optimization. Different methods are there, so that for this particular target application, you create a minimum set of features. Suppose you have 120 features, and in case of pattern classification, maybe out of this 120 features, some features are not having good correlation with the output. So in that cases, you can create a rank of these individual features and say you can take most significant, say 50 features or 30 features, which provides you a good classification accuracy. So there are many methods like filter methods, wrapper methods, by which this feature elimination or feature minimization can be done. Then the classifier, whatever is the classifier, that will basically work on that reduced set of features. And as far as the signal quality assessment is concerned, either the classifier will tell us whether to discard the signal or to accept the signal or compress the signal for further use. So this is the typical signal flow of a CI based signal quality assessment of variable biomedical signals. Any questions?
Participant, is there any question?
Okay, fine.
Someone, let me let that person. Sorry.
Okay, let me proceed if there is no question. So I will quickly go through some basics of these feature extraction tools. The most common feature extraction tools, if we talk about linear feature extraction tools, this is the principal component analysis. Principal component analysis basically is based on extracting the hidden representation of the signal for multiple measurements. So when we apply this PCA, we need to have at least some multiple measurements. Now the question is, when we are measuring a single channel signal, how to make those multiple measurements? So the basic trick is you chop the measurement, say every 3 seconds, 4 seconds, or 5 seconds, and as if you are making some multiple measurements. Number one. Number two is that these measurements must have some basic correlation between them. If the data is not correlated or uncorrelated, there is no use of making the PCA analysis. So the most common approach of PCA is eigenvalue decomposition of the covariance matrix, by which we get some principal component scores, and from, if you project your data matrix, if taken data measurements on these individual principal components, then you can get the feature vector. This feature vector which can be fed to the classifier. The second one is discrete wavelet transform. The basic of discrete wavelet transform is that it basically exploits the time frequency localization property of measurements by checking its similarity by sliding a compressed and dilated version of mother wavelet. So there are different types of mother wavelets available, like I think most of you have heard about Haar, Dubachis, Coeflet, different types of mother wavelets are there. So basically it is a sort of filtering, sequential filtering, high pass filtering and low pass filtering, and each stage you will be getting a set of coefficients. One is called detail coefficients, which provides high frequency, and another is called low frequency components. Now, since most of the biomedical measurements are biomedical signals are low frequency signals, so normally what we do is that in the case of dyadic decomposition, we always follow the approximation coefficients for successive decomposition levels. I will quickly go through these things because I think these are all known to all. These are very common. This is a nonlinear feature extraction tools. Feature extraction tool, we call it a stacked autoencoder. Now, in the case of a stacked autoencoder, there are two parts. One part is encoder and another part is decoder. So if this is my input signal, then basically an autoencoder provides us a compressed representation of the signal by encoding it through different layers. These layers are called hidden layers, just like an artificial neural network. And each stage there is a summation, weighted summation of the inputs, and some bias will be there. And before using an encoder, basically it is trained, and where the input signal is reconstructed at the output based on some cost function. Normally in case of these signals are MSE or MSE, some value, some low value of MSE or mean square error or root mean square error, these are considered as the basically the cost function. So when the encoder is trained, this decoder has no function. So for an unknown sample, we can simply apply the input and tap the features. So these are the functional representations of these encoders and decoders, and this is the representation of MSE. This stacked autoencoder, the basic unit is an autoencoder. When we cascade these multiple autoencoders, one cascaded by the others, then it is called a stacked autoencoder. There are many other versions of stacked autoencoder like denoising autoencoders, where at each stage some noise intentionally some noise is mixed. So I will be quickly go through this feature extraction and pattern classification tools basically. So in the case of pattern classification, what we do is that we extract features from the particular segment of the biomedical signal. Then we feed this to a classifier, and the classifier is having some parameters and some other parameters like hyperparameters, and this classifier, when it is trained using some reference data, in our case of signal quality assessment, obviously this training data will be the annotated data. Okay, so basically the essence of the classifier is that this transformation is non-linear, is the model is represented by G. Basically all classifiers do not make a linear transformation. Okay, so the objective of a pattern classifier is to achieve the minimum and optimal values of weights and parameter biases, and some hyperparameters are there, like how many number of units, hidden layers, activation functions, learning rates that we are using. Okay, so this is basically the objective of pattern classification tools. So as far as signal quality assessment is concerned, the objective is whether my signal or the segment of the signal is having good quality or bad quality. So if our objective is that we will only capture the good quality, then the target class will be good quality. If our objective is to capture the bad quality, then the target class will be bad quality. Like here I have given, this is very naive, in fact, evaluating how we can evaluate the classification performance. So I have shown one example. So if we only target the corrupted class, then corrupted will be taken as positive, and acceptable class, that means the class with good quality, will be taken as negative. I have given this an example case. Suppose we are considering 100 cardiac beats where 12 are corrupted and 88 are acceptable, or that is the ground truth. How we can create a confusion matrix? I think these things are known to you. Only for the sake of discussion, I just included it. I think I can just skip it, because true positive, false negative, and all these things like sensitivity, predictivity, and these are the parameters that we normally use to represent the evaluation. If to evaluate the performance of a parameter, this classifier, I think these are known to you. Dr. Chaskar, should I skip these parts? I think these are
Yes,
common.
yes, sir. They have covered all these things.
Fine, fine. So only just for the sake of discussion, I just included these parts. So I will be discussing very quickly some pattern classification tools. I start with K nearest neighbor, where basically I have shown 3 classes, and for an unknown sample we will be calculating the distance of this unknown class with each of the samples of the trained class, and based on this we will make a decision. Basically it is a voting that is taken. So the value of k nn, the value of k, that can be 3, 4, 5. In the case 3 is k, the value is 5. That means most nearest 5 samples will be considered like this, and based on that there will be a voting that majority of the classes that is inferred by the classifier will be the class where this unknown sample will be assigned. Okay, next one. I think these also have been already covered. Then comes logistic regression. In the case of logistic regression, we have a S or sigmoid type function. This is the function, and if we take a threshold value of 0.5, then above 0.5 we can take it as 1, and below 0.5 we can take it as a 0. So it is very simple to use a logistic regression for a pattern classification problem, because this function provides us a value of 0 and 1, and in most binary pattern classification problems these classes are assigned as 1 class or 0 class. So by using a proper threshold, basically we can use this logistic regression as a pattern classification tool. Support vector machine is very useful. Basic objective is to construct a hyperplane. I think this is also covered in some classes. Basically these are the nearest objects or samples from this hyperplane that is dividing the 2 classes, and based on this the training of the classifier, that is weight and bias, only to just change the inclination of the boundary, this slope of this hyperplane, so that it provides a margin. This M is the margin. This is guided by this 2, and this is maximized. Sometimes linear hyperplane is not possible. In that case, some kernel functions like Gaussian polynomial functions, these are basically used to map the data in some multidimensional space where we can have an easier this separability between the classes. I think all these have been also discussed. The last one is random forest classifier, where the basic unit is decision tree, where this is the root node, and we can have a progressive classification, and each level there are, I think you know, this entropy, then this information gain leaf node and all these things. So at each level we can have a split of decision. So if we take a master feature set having n number of features, and we need to assign a particular sample in A, B, C, like good quality, medium quality, or corrupt quality biomedical signal, naturally what is done is that different combinations of features are provided, are taken, and each decision tree can provide different levels to a particular sample. So in the case of blind test, this decision is taken by a majority voting. So in the case of random forest, we can consider random forest is an agglomeration or this combination of many decision trees, where the individual decision trees will provide us the individual decisions which can be asymmetric in nature. So the advantage of this random forest classifier is that it requires less training, and the unique feature is that if for some unknown samples some feature is missing, say here one feature is missing in the unknown sample, then also only this random forest can provide you consistent accuracy. Okay, so I think I have covered first part, I think, of my discussion, part A. So if you have any questions, you can ask. Let me just admit that I am not a very good expert of machine learning techniques. Many of my, whatever I am showing you, these are basically works in the second half. What I will be showing is basically some works of my PhD scholars. So if you have any questions, you can ask me right now regarding the part A. So in this part, I will be discussing on few applications. One is unsupervised learning based multi-class PPG signal quality assessment, supervised learning based multi-class PPG. So most of my discussions will be on PPG. Okay, and I will discuss some of the works we have already done in this area. Okay, so let us start with first one. The first one is that when we are talking about the data, the annotated data, getting annotated data is very difficult. So what we have done is that in our laboratory, we have created one annotated data. So in this, on the left side, you can see that we have collected some real-time volunteers data. So the basic idea was that we are using a BioPack MP45 two-channel data acquisition system, and this is one PPG, wrist-worn PPG sensor. And on the other hand, that is the right hand, we have used a accelerometer sensor, 3-axis accelerometer sensor, and from that data, using a simple National Instrument DAC card, we have simultaneously acquired the data. So in this side, we had the BioPack Students Lab software for data acquisition, and in the accelerometer sensor, we have the MATLAB data acquisition toolbox, and there was some synchronization pulse used to just synchronize the data. So if this is the reference PPG, that is the clean PPG. So what we did is that we kept this hand where the PPG data, PPG sensor is collected. This was kept stationary, and this hand was moved. Okay, and by this way, by adding these two, we generated this image corrupted PPG signal. Okay, so in the first case, we had arbitrary hand movement in single direction. This is the data we got. The second one is if you use a low cost PPG sensor that is available in the market, then if we can keep this hand stationary and keep this hand movable in arbitrary direction, then you can also use a single dash card and collect the data in MATLAB or any other environment. So here we used 3-directional data movement to get a controlled motion artifact PPG data. And if you want to use public repository, then Mimic 2 or Mimic 3 data under Physionet, I think many of you are very familiar with this Physionet data. www.physionet.org, that is the website, and complex system laboratories dataset, that is another dataset that is available. So from these dataset repositories, we can also collect many data. And if you follow there in the website, I think some open data is available on signal processing, IEEE signal processing cup from the year 2001, I think, till now. Each year they publish one challenge cup data, and from that data, all these data are annotated data. I think in 2014 or 16 there was a challenge regarding this signal quality assessment on ECG signal. Okay, so these are basically some web-based resources wherefrom you can collect the data for validation of your signal processing tools. So the first work of us, this is the paper, I have given the references. So this is the PPG data. We took 5-second window and we use some entropy features. So basically entropy is a measure that gives you the measure of internal disturbances within the signal, and some statistical features, these were also taken, and some combined feature set was formed. And this is a self-organizing map. I think you are familiar with this self-organizing map. And from this self-organizing map, we classified the data as clean ECG, moderately corrupted ECG, or highly corrupted ECG. Okay, so this was one work that got published in IEEE ADBLAT's Signal Processing Conference. Now, considering the features, we took altogether 7 features. So this is a plot where the different combinations of the features were considered and the accuracy was plotted in y-axis. Okay, so you can see that from this diagram, around 92% of accuracy was obtained when we consider the feature combination of 3, 4, 5, 6, 7. These features when combined. Now, this is a plot of the signal where this PC stands for partly corrupted, and in the bracket, that is the true data, and PC, this out of the bracket, whatever is written is the calculated data. So the ground truth is given in the bracket, and outside the bracket, you can see that there are some misclassifications like here and here. There are some misclassification cases where there were errors. Okay, so these are the corrupted segments. Sorry, these are the corrupted segments. These are the partly clean corrupted segments, and these are the perfectly clean segments. So I have shown a very simple visual representation of from 2 subjects. We collected some 20 subjects with healthy control and 20 subjects with cardiovascular disease. These are the features. You can see that extensive use of entropy features were used, like approximate entropy, sample entropy, spectral entropy, permutation entropy. So if you go through the literature of signal quality analysis or assessment, you will find that these entropy features have become very, very popular. And these are some statistical, like detrended fluctuation analysis, fractal dimension, then Higuchi fractal dimension. These are the features. So using this 7 set of features, we could achieve an accuracy, multi-class classification accuracy of around 92%. Okay. Then comes the supervised learning based multi-class PPG signal quality assessment. Here, the approach is little bit same with the earlier one, but the difference is that here we used supervised learning, like in a self-organizing MAM, it is a competitive learning approach or unsupervised learning approach. Here it is basically here the classifier what we used is a supervised type. Okay, so in this work we took 3-second PPG frame, considered some statistical features like standard deviation, max, mean, and in the case in other domain features like from the FFT, first Fourier transform, we took skewness and kurtosis. Probably in part A I mentioned that skewness and kurtosis are very, very important, but here the skewness and kurtosis are used not directly on the signal or its sample distribution. Rather, the FFT of the signal was done and then the skewness and the kurtosis were calculated. We took 2 entropy features. One is spectral entropy and approximate entropy. Constructed the feature set consisting of these 7 features. Then we classified the data. This is published recently in a journal, Measurement Science and Technology. So here random forest provided the best results. Okay, so I have shown the feature combinations and the corresponding. You can see that using this F1, F2 and F3, these 3 feature sets, we could get 97%. This is very important, as I will show you that we could develop a standalone embedded system using a Raspberry Pi to get this classification done. Okay, so we used 4 data sets for evaluation. One is volunteers data collected in the laboratory, then mimic 3 data set, then CSL, and the data set 4 was a combination of this 1, 2 and 3. And in the case of CSL data, we got 100% accuracy. Yeah, you can see that this is very interesting because we could use a simple Raspberry Pi 3B plus board to get this level of accuracy. This is the screenshot of Raspberry Pi in Python environment. So it shows that these are the number of segments, and it is telling whether it is a noisy data or a partly clean data or clean data. Now this type of application is very important, like whenever you are using a standalone embedded system. So in ideal case, this embedded system or the Raspberry Pi will be clubbed with a real PPG sensor with a signal conditioning unit. And if you want to develop a real-time signal quality assessment, so this type of tagging, like annotations, this will come to help when you are doing some offline analysis. So that means the tagging is done at the point of measurement. You can see that in the case of this random forest, we get highest accuracy. The latency for 3-second data was only this 0.1 second. You can see that this is very good in terms of in a standalone system. We used other classifiers like SVM, KNN, and decision tree, logistic regression, but these provided somewhat inferior results. Okay, and this is peak memory requirement KB, because when the code operates, basically the peak memory requirement fluctuates depending upon which type of operation is being done. So this is the peak in terms of peak memory requirement. So you can see that only 19 KB of memory is consumed, including the 3-second data, having 12 bit of resolution. Okay, so that means it is a great savings on your memory also. Any questions? I have showed two applications. Any questions or queries? Okay, let us move on. The next one is the next one is our work that was improving PPG based measurements against motion artifact corruption using supervised MLPNN. I think MLPNN is very common and known to all. Multi-layer perceptor neural network. It is a simple network having number of hidden layers. So this is, I think I have shown from the paper, this is the total flow diagram. Just a minute. Yeah. So this part you must look at. So here the PPG bit delineation was done. Okay. So sorry. So bit delineation was done. From that, each of the bits were fed to this multi-layer perceptor neural network, and from this, basically, the clean or corrupted segment, this was classified. The later part of the work basically showed how we can eliminate or minimize the effect of this motion artifact corruption by correcting the bit morphology using an autoencoder followed by a multi-layer perceptor neural network. I am just showing you the basic philosophy. So in this diagram, you can see that, so this is the reference signal. Always we need to show the reference signal. And this is the noisy signal. So you can see that here and here, the signal is corrupted, fully corrupted almost. Now, the basic notion was there that if this is the reference bit, this is the blue color, this is the reference bit, then we can correct this bit format by multiplying each of the samples with a weight factor, and these weight factors are provided by this multi-layer perceptor neural network. That was the basic notion. So by this way, you can see that the corrupted bit, this one, this corrupted bit was corrected and smoothed using this approach, just by simply multiplying each of the samples of a bit by a weight factor, so that it resembles the shape of a clean PPG. This is basically the notion. So by this way, we can show that we showed that an improvement of crest time. Basically, the crest time is, if this is the PPG bit, the crest time is basically this time, the gap between the PPG foot and the systolic peak. So in these cases, you can see that due to the uncertainty in measurements due to signal corruption, the crest time cannot be measured properly. So by this way, we could improve the measurement by 38.2% of crest time for healthy control and 33.1%, 0.1% for CVD group. A by B ratio is basically the ratio of heights of the systolic peak and the dicrotic notch. This is basically used for calculating the augmentation index. Okay, so for this, when the bits are corrupted, like here, you cannot see the dicrotic notch at all. So when we have such type of improvement, say like this is the reference signal, clean signal, and this is the reconstruction by the proposed artificial neural network. You can see that this noisy signal, these noise portions are now gone. So we have a smooth and clear this PPG signal. So by this way, we calculated, we considered only two parameters like crest time and A by B ratio that is used for augmentation index, and we could see that we could achieve this 50% improvement for the case of healthy control and 42.41% for the CVD group. Okay. The next application is predicting missing data based on history. So this is the third case study I will be considering. The concept of missing data is that, suppose we have a data, like this is a data I have, and this portion of the data, like up to this, is considered as a missing data. This missing data on PPG can occur due to the loose contact of the sensor. Suppose a person lying down on a bed is wearing a PPG signal, but somehow the cap has detached from this fingertip. So in those cases, there may be momentary loss, that is momentary make and break between the contact of the sensor and the skin. So there can be an unreliable data or a completely missing data. So the objective of this job was to predict missing data, but here in missing data, the signal quality assessment was cleverly used. Let me first show you the result that if this is the missing this history data, so this is the good quality pulse and these two are the bad quality pulse, then from using this two good and two bad quality pulses, our algorithm could predict around 40 to 30 to 40 pulses in the missing segment of the pulse. So what we did is that initially we had a signal quality assessment. Then based on this, we could predict the missing data based on history of the same channel data. Whereas where the history can contain, as I have said, some corrupted data, some healthy data as well. So this is basically the signal processing flow diagram. So this is the first part where we developed a PPG reliability assessment model by using a stacked denoising autoencoder. The objective of the denoising autoencoder is that at every stage we mix some noise with the data and then again feed it. So this stacked denoising autoencoder is followed by a multilayer perceptor neural network where we are jointly training both of these in single epoch. That means normally what happens is that when you train one unit like MLPNN or an autoencoder, it is separately done. But the unique thing that was done here is that the training of the SDAE and the MLPNN was jointly done. That means in a single epoch, the weight and bias of this MLPNN as well as this weight and bias of that encoding part and weight and bias of the decoder was changed. Okay. Based on that, basically we categorized the data as acceptable or motion artifact corrupted, and that basically provided a prediction data stack based on which we developed one missing segment prediction model based on some deep learning tool which is called long short term memory or LSTM. So here I am not discussing this part because this has nothing to do with the signal quality assessment, but I have discussed this portion that for missing segment prediction from the same channel data, the signal quality assessment can be an useful tool. Okay. So here I am showing that as the number of missing bits in the top chart, with the number of missing bits increasing like 5, 10, 15, 20, you can see that the correlation between the reference bit. So here we have reference PPG data and this is the predicted PPG data in green color. So if we plot the reference data, we make a correlation with between the predicted PPG and the reference PPG. As the number of bits increases, naturally the correlation will fall. It is not possible to have 100 seconds of data prediction based on only 4-bit history. So naturally after 40 bits, you can see that the correlation is now little bit down. And on the other hand, this RMSE, that means root mean square error or this mean absolute error, they increases. Naturally, the error will increase. So lower the length of the prediction segment, higher will be the correlation and lower be the error. So one volunteer data, CVD data, that means cardiovascular disease data, and one CNC data, Computing in Cardiology is a conference that is around 20 year old. So some open data is available in Computing in Cardiology database, where from we took another data. So for that, we show the reference PPG data and the predicted data. You can see that the correlation is quite good when we are missing around, say, 20-25 bits. Okay. So this is the experimental result. Any questions? Any questions from the audience?
Sir, I think there is no question from audience. I could
Okay.
not see any question in the chat box also.
Fine, let me proceed. So this is basically in the second part or part B, I am showing some case studies, what we have done and possible ways of doing this type of things. So on the last one, that is this prediction of missing data based on history, we could develop a standalone system. See, this PPG sensor is available in the market and some online stores, you can procure it. So this is the signal conditioning unit that is available with the PPG sensor. The only thing you have to do is that from this signal conditioning unit, you need to feed the data in the Raspberry Pi board, where this is the board. Now, this Raspberry Pi board is not having any inbuilt ADC. The best solution is either you can procure one ADC complying I2C bus protocol or say SPI bus protocol. So we used this ADC. Let me just write down here if it is legible. MCP 3202. This is an ADC complying SPI bus protocol. From that SPI ADC, we could directly feed the data, and you can see that this is a variable solution we have developed. So if you have a PPG and if your PPG is having a momentary loose contact resulting in missing of some bits, then using this technique, in that prediction, whatever I discussed, that prediction is occurring in on device. That means within this Raspberry Pi, it is able to reconstruct those 30-40 missing bits, and then it is only transmitting. So before this prediction, basically a signal quality assessment is done. Here in the right side of the screen, you can see that this A represents, this is the data logging part. So as per bit sequence number, the first bit is acceptable, the second bit is acceptable. Likewise, the unacceptable bit starts from bit number 7. So MSC means motion artifact corrupted. Okay, so from here this reconstruction starts. So rec means reconstructed 15, 16, 17. So this portion basically shows the bits reconstructed. Okay, and that reconstruction has been done based on a stack history that can contain maximum 2 corrupted bits, because more the corrupted bits will in the stack, less accurate will be your result. So it is possible to develop variable solutions, because you can see that this arm can just put it in an arm. This is a laboratory type prototype. We could not develop any commercial type because that is not possible in our laboratory infrastructure, but it is possible to have a lower version of the Raspberry Pi, like Raspberry Pi 0W or something. So the space can be much lower, because in the case of Raspberry Pi, what I found is that there are some LAN ports, USB ports. These are basically that not much useful. So if you want to develop better, if the memory permits, you can take a Raspberry Pi 0W, because the space will be around less than half of the space. Okay. Now I will show you another application that was developed by us for continuous monitoring applications. So this is basically signal quality aware based continuous monitoring applications. You can see that I have tagged the different segments. Like here, the hand was stationary, so we have good quality pulses. Here, sudden hand movement. So here you can see that there is some glitches, abrupt fluctuations in the PPG. Then we have some low amplitude hand movement. Again, the hand is stationary. So we repeated this cycle using this variable type PPG sensor. So the basic flow was that we will collect the data from the PPG. Then we will make a binary classifier to tag it as usable or unusable. So if we get an unusable signal, then we will simply discard it, just throw it away. Using the usable signal, then we developed a vector quantization based compression and residual encoding strategy, and then we streamed the data using a Bluetooth type AC05, I can't remember exactly, AC05 or AC06 Bluetooth module. So the basic thing was signal quality score. Here I have shown some signal quality score and kurtosis values. So what we did is that we took correlation, kurtosis, and using a combination of them, we could develop a signal quality score, and we took some heuristic calculations on around say 100 number of volunteers to take the initial values like this and this. Based on this, we took thresholded, we took some limiting values of P and Q, like this P and Q we chose, and based on that threshold, we could make a simple binary classifier based on this SQS, correlation and kurtosis. So based on that, what is more interesting here is that you can see that here we took 3-second data. So here this is the corrupted pulse, this is the qualified pulse, this is the corrupted pulse. This is an FP case. False positive case means it is basically a case where we have a false positive. That means my algorithm took it as a positive, that means qualified segment, whereas it is not a qualified segment. That means here the corruption level is high. So this is a false positive case. On the other hand, this is a false negative case because my algorithm predicted it as a corrupted segment, whereas I have ample number of good quality pulses. So these two cases I have shown. Obviously, in many, how much accurate you want to develop your algorithm, there will be some errors. So algorithm, these classifier errors are basically these false positive and false negative cases. What is more interesting that I wanted to show you is that you can see that if we take this is a graph where I have shown that good quality pulses to bad quality pulses. So this 100 shows when we have 100% good quality pulses, and here when we have 0% good quality pulses. Sorry, I'm sorry, just reverse I have said. So this is 100% corrupted pulses, and this is 100% good quality pulses. We connected a USB type meter to calculate the energy that is being drawn by this sensor, and using we calculated the longevity, that means what is the battery hour that is provided by this sensor. So when we have 100% corrupted pulses, the battery lasts for about say 4.92 hours, and when we have good quality pulses, the battery lasts about say 5.76 hours. So you can see that when we are in a continuous measurement scenario, signal quality assessment not only provides us good measurements, but also it discards, if we can discard selectively the corrupted quality pulses, then we can also enhance the longevity of the battery powered applications. Like this one, we used a 2200 milliampere hour lithium ion battery. So you can see that when we have 100% corruption and 100% clean data, so the longevity in the battery occurs. So these are the intermediate values like 90%, 80% and all these things. So there comes the utility of signal quality assessment in continuous measurement applications. Okay. The last one, this we have developed, this is yet not published. I will show some results. So blood pressure measurement is one emerging area of research, and PPG based or ECG PPG based blood pressure measurements are getting very importance nowadays, because due to the popularization of this wearable sensing, now we want to have a continuous measurement of blood pressure. Now you can see that this is the ECG and this is the arterial pressure waveform. Now if we draw a PPG waveform here, you will find that the PPG waveform will look like this. So most of the research that has been done on this arterial blood pressure measurement is based on a parameter which is called pulse transit time, PTT. Basically, pulse transit time is basically provides us the gap between the ECG peak and the systolic peak of the PPG, because if we consider the blood pressure as a wave, then the wave starts from the aorta when the ventricular contraction starts. So the blood pressure starts from the aorta and through this shoulder, hand, it reaches our fingertip, and that takes some finite amount of time. So basically most of the non-invasive blood pressure measurement methods till date available mostly utilizes is PTT. There is another version which is called pulse amplitude time. But the problem with the ECG is that you need to connect some chest leads, and it is cumbersome for the subject. So after 2010, 2012, the researchers started working on only PPG based non-invasive blood pressure measurement. So if this is a single PPG pulse, then you can see these are the many features which have been used by various researchers to make a non-invasive blood pressure measurement from the PPG cycle features. So these are the various widths and the different heights of the systolic peak. Okay, so based on this, the blood pressure measurement techniques can be divided into two categories. One is that simple blood pressure measurement where we have a 30 to 45 second interval. We will get a single blood pressure measurement. And the next one is that beat to beat blood pressure measurement, where the measurement is done over each cardiac cycle. Okay, so in our work, what we have done is, I will show that this is the scheme of our work, but let us see what are the issues. So I have shown here some low quality pulse waveforms. So here we can get one pulse, maybe we can consider this pulse, we can consider this pulse. So these are the qualified pulses. So these are the qualified pulses. I am denoting them as Q. This pulse is also qualified, but none these pulses, these are simply unacceptable pulses. Here also you can see that there is a momentary saturation. Then some of these pulses are qualified pulses. But if we want to make a continuous BPB bit to bit blood pressure measurements, then this intermediate, this bad quality pulses like here or here or here, they create a hindrance, because in the case of bit to bit blood pressure measurement, you cannot afford to lose data. Okay, so these are basically some good quality pulses, and here you have one good quality pulses, and rest are basically garbage. So here you have some good quality pulses, but the rest is garbage. So when we talk about bit to bit measurement, it is very important to have at least say 10, 15 or 20 number of PPG pulses. So to have a reliable bit to bit blood pressure measurement, first we have to assign the reliability factor on the PPG pulse quality that we are getting. So here is the application. What was done is that signal quality aware bit to bit blood pressure measurement. So the first thing that was done is that this is the noisy PPG signal, and this is basically the SQA block. Here the feature extraction was done from approximate entropy, spectral entropy, then George parameter, and Iguchi fractal dimension for every 3 seconds of data using a self-organizing map. Find that this is a unsupervised pattern classifier. Okay, so this basically provided whether this 3 second data, whether it is a clean segment or a corrupted segment. If it is a corrupted segment, there is no use of using this data. You can simply throw away this data. Then from this clean segment, using a time delay neural network, we extracted the prediction. We predicted the blood pressure, and here we also used this recursive feature elimination, which is a rapid type feature minimization technique. Here from each of these features, from each of these bits, we calculated the systolic blood pressure and the diastolic blood pressures, and for that we took few time domain features, statistical features, wavelet fit features, and autoencoder based features. Then from this combination, we use the recursive feature elimination to reduce the number of features by around 50%. But the beauty of the thing is that till now, most of the researchers did not provide any attention for this SQA block. So whatever research is available on this bit-to-bit blood pressure measurement using PPG, only the good quality segments of the PPG were considered by the researchers. This is good, but in real-time measurements, you never know what is good quality pulse and the bad quality pulse. So the best way to have a reliable bit-to-bit blood pressure measurement is to assess the quality of the pulses before you predict the blood pressure. So that the result is that we could improve the accuracy by a factor of around 20% for systolic blood pressure and around 25% for diastolic blood pressure from unknown motion corrupted PPG data. So that is the advantage. So now I have come, I think I'm 15 minutes late anyway. So with this, I would like to summarize what we discussed today. The first thing is that SQA, or the reliability assessment, plays a vital role in improving the measurement accuracy for variable biomedical measurements. So today, whatever I discussed, these are in terms of all variable biomedical measurements, and many cases, these variable measurements can provide uncertainty due to the loose contact of the sensor or the motion corrupt level. Now, the second point is what I discussed is that on device or point of contact, point of measurement SQA can save pre-processing power consumption. So any further automatic measurement, if we can do a signal quality assessment, then the unnecessary power of processing a signal can be saved, and this saving can contribute to the final longevity of the battery driven devices. Okay, now for wireless monitoring application that I have shown as the compression work of our. So wireless monitoring applications, the unnecessary transmission of corrupted unacceptable segments can be avoided. Okay, now another conclusion we can draw from that, this is a good area you can take up, because in this area no research is still not available. So for improved measurement, if a confidence value can be associated with the measurement quality. Suppose if we talk about the last one, the bit-to-bit blood pressure measurement. So if we can devise something that we will be measuring the signal quality bit by bit, and we will also calculate, instead of discarding the data, we will also calculate the blood pressure from each of the bits and provide some confidence value. So for example, when a bit appears to be partly corrupted, I will say that whatever blood pressure value I am providing is 60% accurate. So for all of these bits, I will be providing some measurement. For example, for this case, it is a systolic blood pressure and a diastolic blood pressure. But I will provide also, based on the signal quality, a confidence that will provide the end user how much to consider from these corrupted segments. But still, I am not discarding all the segments. As we have done in our research, we have discarded the segments. So instead of discarding, if we can associate one confidence, this can be done by using simple fuzzy logic, I think. If you can develop, this is an open research problem, I am telling you. If someone, if you interested, you can do it. This will be the first of its kind. Like in case of blood pressure measurement, there is no paper till date which provides a blood pressure value with some confidence. Okay, so these are the summary of today's discussion. I would like to acknowledge these persons who are my research scholars who work with me in our laboratory in these areas, in signal quality assessments. And these are the references I would like to share, because these are basically books, not any papers, because Dr. Chaska told me that there may be some MTech level students. So if you can take a screenshot of this, these are the basic books which will give you a basic details, basic and advanced details of biomedical signal analysis, like this one, Semlu and Griffel. Then this is a book that deals with different computational intelligence applications in biomedical engineering, starting from cardiac signal to brain signal to MRI signal. Okay, this is a signal. This is an old book written by Leif Solmo and Pablo Laguna. This deals with EMG signals, then ECG signals and EEG signals. EEG signal processing you will get here in this book. You will get ample examples and case studies of EEG signal analysis. These are the books that will give you the foundation of this artificial intelligence applications or machine learning applications. Mostly this is for mostly for ECGs, and if you want to have some idea on this wearable technologies where you can develop some on-device measurements, then this book this number 6 book may be very useful, because here the guideline for developing standalone applications is provided. Okay, so with this I would like to conclude my presentation. So any questions you can ask me. Okay.